But there's a USB. Thank you. Yeah.
All right, welcome back everyone for the last session of the day on diffusion models and sampling. First up, we have Minghui Jiang, who's going to tell us about taking walks for sampling for truncated log concave measures. Take it away, Minghui.
Thank you. Good afternoon, everyone. This is a collaborated work with Yuan Sichen, and we are from the same institute, Seminar for Statistics from ETH Zurich. And this is the setup for our problem. First, we have the target distribution. We want to draw sample from this density. We have this pi x proportional to exponential to the minus fx. So this part is very like standard, but we multiply like one indicator function of polytope k. So that means we want to draw samples from this distribution truncated on this polytope, and this polytope is defined by this matrix inequality, Ax greater than B, and A is m by n dimensional matrix, B is m dimensional vector, and we assume f to be a like second order differentiable function. Some other assumptions on f. The first assumption is like strongly log concave and strongly log smooth. We suppose there exists beta greater than alpha greater than 0, such that the Hessian of f is lower bounded by alpha and upper bounded by beta. And we define the ratio kappa, like beta over alpha, to be the condition number of f. And then for assumption 2, we weaken the assumption a little bit. So we still assume log smoothness, so there exists beta, so that the Hessian is upper bounded. But we only assume that the Hessian is positive semi-indefinite, greater than 0. Moreover, we assume the target distribution has a finite second moment, and the covariance matrix of it is upper bounded by eta I. Or you can treat eta as the largest eigenvalue of this covariance matrix. So there are a lot of examples of those kinds of target distributions from like statistics community. First, it's the Bayesian probit model from this Anchesky and al. Paper. Basically, like for the Bayesian probit model, sampling the posterior reduces to sampling from this distribution. Here, sigma is a given covariance matrix, and it is truncated on this polytope, like each component is greater than 0. Note that this polytope is not bounded, so our result, yeah, also works for that. And for this case, for a truncated Gaussian distribution, we can always reduce to kappa equals 1, which means like after an affine transformation, this part becomes this standard normal distribution. But then we have a new polytope. The polytope has the same number of constraints and in the same like dimension space, Euclidean space. And this is our framework. We measure our mixing time by TV distance. So basically, like the smallest step, such that after these steps, our distribution is epsilon close in terms of TV distance to the stationary distribution. And this is, we also assume a warm start, which means like we get a not so bad initial distribution. Like mu0 of A is upper bounded by m times target distribution of A. So this is our algorithm. Like, basically the intuition is that given this convex body K, at each point we define a positive definite matrix to describe its local geometry. And like this is our algorithm. Basically, given each current step, we draw next step from a normal distribution, but the covariance matrix is changing with the current step. And then we add a Metropolis-Hastings filter so that just to ensure the stationary distribution is the target distribution. Like this is some illustration. When x0 is very inside the polytope, you have a larger ball, and when you are close to one of the boundaries, then the local like ellipsoid is also skewed in that direction. So this algorithm works well for the uniform sampling, which means when f is always 0, then for such a polytope, you can prove the mixing time is big O tilde m times n. M is the number of constraints, and n is the dimension. And you can also tune the mixing time dependency upon m and n by imposing some weights on each of the like constraint. So if you put Vidya weights, you have a mixing time of like m to the 0.5, n to the 1.5, and then if you put approximate Jones weights, you have a dependency of n to the 2.5, like not really depend on m. So for the non-uniform distribution over K, when f is not always 0, like this Mangubi and Vishnoi proposed this like regularized version of thinking walk called soft threshold thinking walk by adding this lambda I to the logarithmic matrix. So their result is like they assume the polytope K is bounded in a ball of radius R, and f is beta smooth. So they proved a mixing time of mn times plus n to the times beta times r squared. But in our application of Bayesian probability model, K is unbounded, so this does not work for our case. And very recently, Cook and Van Pala like used a different approach. For the special case of quadratic sampling, for f being quadratic, they proved a mixing time of mn plus n squared. Here's our result. We used the Mangubi and Vishnoi regularized version, the same matrix, and we proved the mixing time, like under the strongly low concave assumption, is m plus kappa times n. So first, it removes the R-boundedness in Mangubi and Vishnoi, and also for the quadratic case, kappa can be reduced to 1 after an affine transformation. Then it would be like mn, so removes the n squared dependency in Cook and Van Pala. And we can also extend our result to the weakly low concave case. So in this case, alpha is 0, so kappa just becomes beta times eta. Eta is like upper bound of the covariance matrix. So first, this recovers the strongly low concave bound and also recovers the bound of this like bounded version in Mangubi and Vishnoi, because you can always prove if a target distribution is bounded inside a ball of radius r, then of course its covariance matrix is upper bounded by r. This is one key innovation in our, or to put it modestly, some new observation in our proofs. So basically, for such a target distribution, exponential minus fx 1k, then this, if you decompose this k to 3 measurable sets, then pi s3 is always greater than d times s1, s2, pi s1, pi s2. And the distance is defined by the maximum of the like a Euclidean distance and the cross ratio distance. So basically, the cross ratio distance is dependent on this convex body K. And we can also extend this result to the weakly low concave distribution via stochastic localization. Yeah, some other contributions in our paper. First, if we do not use logarithmic matrix, but use Lewis weights like on this matrix, then we improve the mixing time from this mn to like n to the 2.5. Also, we provide some practical worm initialization. And another result is that like given that only O1 number of constraints intersect the high probability mass of the distribution, the mixing time is like linear in M instead of Mn. This is a reference, and thank you for your attention.
Questions from the
Thank you for interesting talk. If the domain is a convex set but not a polytope, do the results apply?
A polytope is a special case of a convex set.
Right. If the domain is a general convex set, do your results apply, or is it not immediate?
Like, yeah, that's a good point. Like when it's a convex set, I think you need to assume some like regularity conditions so that you can have a good barrier function to define your local ellipsoid or local matrix. Like improving the mixing times, you need the local matrix to satisfy certain continuity like property. Yeah, I mean, like Cook and Van Pala, they have results for like quadratic constraints, not only linear constraints. So our result can also like work for these quadratic constraints, but we just don't list it in here.
Thank you.
Okay, let's thank Minghui one more time.
Thank you.
All right, next up we have Yuhan Wu, who's going to tell us about the regularizing effect of large step size in denoising score matching.
Yes, thank you for the introduction. My name is Yuhan, and this is a joint work with Pierre, Girard, and Claire. This work is about preventing memorization in diffusion models. So I know probably all of you are familiar with the notion of diffusion models, but just so that we're on the same page, the diffusion model is, the goal of the diffusion model is to learn the distribution p-true of images, and it comes from the following observation. We can reverse the forward SD, which is written here, by the backward SD, and the forward SD is just by gradually adding noise to images. But we cannot just reverse it out of nowhere. The magic comes from this unknown score function, which depends on the data distribution p-true. So to learn the score function, a commonly used objective is the denoising score matching. So for now, for simplicity, we'll assume that we'll fix t, and we'll denote sigma and mu to be sigma of t and mu of t for simplicity. And so the denoising score matching objective can be written as follows. So given samples x1 to xn drawn from p-true, the data distribution, then the denoising score matching objective Rn of s is written as follows. And interestingly, we can actually derive a global minimizer of this Rn by exploiting the convexity with respect to s. And it is written in this form, in this form of fraction, s star, and we'll call the s star the empirical optimal score function. Okay, so now, well, great, we have a score function. Then why don't we just plug it back into the diffusion, and we can just generate samples? Yes, but no. So if we diffuse with s star, then you can see, as in the plot, the blue dots are the training sample, and the green dots are the sample generated with s star. And as you can see, the green dots are just mere duplicates of the blue dots, which is something we don't want. And this is what we call memorization. And the reason of this happening is that S star is the score function of a Gaussian mixture distribution with a component centered at each data point. So our goal is to explain the reason that in practice, even without explicit regularization, we do not learn S star, and there's only a moderate amount of memorization. To state our theorem informally, so we will again be considering the denoising score matching objective Rn over the class of two-layer neural network for one-dimensional data. Then we prove that for a small level of noise and a large learning rate, the SGD on Rn cannot stably converge to S star. Well, in short, without vanishing learning rate, the model cannot fully memorize the training data. Now, to give our result more formally, we consider the model, the two-layer, as I said, the two-layer ReLU network, which is given as follows, and we rescale the output of the model. Well, if you attended the keynote talk of Feng Spark, you'll know that this is due to normalization issue, and we will also have the constraints on weight for technical issues. And also we will be training, as I said, with SGD, with learning rate eta and mini batch estimation RJ hat of Rn. And we'll also rescale the updates by M, the width of the network. And lastly, in order to state our results, we'll need the notion of linear stability. So we say that a local minimum theta star is linearly stable if there is an epsilon, such that if we initialize a theta star within this epsilon ball of theta star, then throughout the SGD, in expectation, the parameter will lie within this epsilon ball. So, well, in short, if it is linearly stable, theta star can be converted by SGD. And to our result states the following. So if we denote delta to be the minimum distance between two different data points, then consider theta star to be a linearly stable local minimum of Rn. There exists, well, so for small enough noise sigma and large enough learning rate eta, the distance between the learned score at the theta star the distance between the learned score at theta star and S star is large, and is bounded below by the quantity on the right side. So in short, this means that large learning rates prevents memorization, prevents us from learning S star directly. And also just one remark on the lower bound is that it actually scales with delta. So if the train data is more separated, the more S theta star is away from S star. Now, to give you an idea of how to prove this, two key points. One is that, as I said, S star is just a score function of a Gaussian mixture distribution, and so as sigma goes to 0, the probability density of mixtures of Gaussians becomes irregular, and hence, well, the score function S star also becomes irregular. And combining this with the following fact that the larger the learning rate, the smoother the learned score becomes. And by combining these two observations, you can prove the results. And lastly, we conducted some numerical experiments to verify our results. The first is that we find that large learning rate leads to less memorizations. So as you can see in the plots in the left-hand side, we trained a model with a smaller learning rate, 0.05, and the sample data points, which are the orange dots, resembles much more to the training data than the plots on the right-hand side, where the learning rate is large. And second, as I remarked before, our results, well, the lower bound in our results scales with the minimum distance between data points. So one way to increase this distance is to increase the dimension. And this is what we found, is that increasing dimension also reduces memorization, as you can see in the plots on the left-hand side. And we trained a model in dimension 10, and the orange dots are also the generated samples, which resembles the training data, which are the blue dots. However, on the right-hand side, where we increase the dimension, the orange dot does not resemble the blue dots anymore. Okay, and just to summarize, so 2 points. So first, we proved that non-vanishing learning rates prevents diffusion model from fully memorizing training data. And second point is that although our study focused on 1D, our theoretical study only focused on 1D data, our experiments suggest that our result may also apply to multidimensional data. And just to point out some further, some future research interests. One direction is to generalize our results to higher dimensional data, and one may also study the effect of the sample size n and the dimension z. And lastly, although our results suggest that larger learning rates prevent diffusion from memorizing its trained data, it does not say that it improves the quality of the images. So one research idea may be to try to balance the learning rate eta and the quality of the generated data. And that's it. Thank you so much.
What are the challenges in generalizing to higher dimension?
Basically, with higher dimension, you will have much more complicated, it just becomes much more complicated mathematically, and it is not straightforward to generalize from 1D to the multi-dimension.
So if your data belongs to a particular manifold, do you know if the generated data will also belong to this manifold, or it would just lie around it?
Sorry, can you repeat your question?
I'm wondering if your data, your training points belong to a certain manifold, for example, certain images, and you want to generate similar images. Does the generated data will be just close to this manifold, or you can expect that it is actually inside this manifold?
You mean our result? Does our result implies that the generated data lies within the manifold or not?
Yeah, what does it suggest?
It doesn't really say this. So that's a good question, and this can also fall into the future research interest to study how learning rates shapes the generated data. However, this is not what we've did in our research. So this is not. So it might. So thank you for the question. It's really interesting for future work, but it is not what we concern. The next one?
The one where it's not memorized. Yes, perfect. So I guess on the right, the generated samples don't represent multiple nodes.
Yeah.
So I guess my question is there in practice a regime where you enter the setting where you don't memorize, but you do actually get this sort of multimodal behavior of the generated samples?
Sorry, can you repeat your question?
So is there a regime where you can prove that like in practice, where you can prove that you do not memorize the examples, but you actually do exhibit multimodal behavior in the generated samples? So I guess like the right does not currently.
Yes, that's interesting. Again, our result does not imply this directly, but that's also an interesting point. I think there's already some work addressing this, but I don't have it in the back of my mind. So yeah, so we can talk afterwards if you're interested.
I see. Thank you.
Okay, in the interest of time, let's thank one more time, and let's switch to the next talk.
Okay.
Okay. The next talk will be Peter Podobczyk, who's going to tell us about linear convergence of diffusion models under the manifold hypothesis.
Sorry, I'm the third guy.
Oh, sorry, George Diligianadis. Close enough?
Yes, very good. Hi, everyone. Unfortunately, neither Peter nor Iskander could make it today, so we're stuck with me. And so I'm going to talk about diffusion models again. So many thanks to previous speakers. So I'm going to probably skip a couple of slides. So I'm going to talk about linear convergence under the manifold hypothesis, and linear refers to the dimension of the manifold.
Can you speak in front of the mic, please?
Yes, sorry. Okay, so this is Iskander and Peter. So obviously we already had an introduction, so I'm going to skip this, but the idea is generative modeling, so we've got access to data from a distribution and we want to learn to sample from an approximation of that distribution. So there's often a couple of choices to make in the forward process, the noising process, so people use typically either the Ornstein-Alemech process or just Brownian motion. And again, we're going to be mainly concerned with the standard score matching objective, which is intractable, but it's a little bit easier to work with. It's equivalent to the denoising score matching objective, but typically in the convergence literature, people just look at the score matching objective. To get the generative model, you take the approximation, so you train a neural network on this objective, you take this S hat, you plug it in, you discretize, and then you sample initializing from a standard Gaussian, okay? So now in the convergence literature, people essentially first assume that we've got a certain error for the score matching objective. So we've learned the score up to a certain threshold epsilon squared, and we want to bound the KL between the generative model at some time t delta and the noisy distribution, the noisy data distribution, after adding a little bit of noise. The reason we do this is called early stopping. The reason we do this is because it prevents memorization, and also it makes things a little bit smoother. So if you want to study the difference from the true data distribution, then it's simply adding a little bit of an extra delta, so that doesn't really make a huge difference. So now there's three sources of error that appear when you're studying diffusion models, when you want to analyze this KL divergence. So the first one comes from initialization and stems from the fact that we're not initializing from the push forward of the data distribution, but rather from a standard Gaussian. Now, in the case of OU, the Ornstein-Alemech process, we know that it converges very fast, but still there's going to be a small discrepancy. The second one, which is much bigger, is the discretization error, which is the one we're going to be mainly concerned with. And finally, there is the score error, which in the convergence literature, if you like, the iteration complexity literature, it is treated like a black box, and we're going to do exactly the same today. So there are results about how well you can learn the score, but you can somehow plug them in with this result, with our main result, to get a complete picture. So there is a lot of work that has been done in this direction, but in the interest of brevity, I'm just going to state in the general case what the state of the art is. Essentially, it's a linear in the ambient dimension. So that's the dimension where the diffusion lives in. So again, this is in KL. Now, there are similar results in a paper by Conforti, Durmus, and Silvery. The issue is that if this ambient dimension is large, and for image data sets, for example, this can be very, very large because it's pixel space, the dimension of the pixel space, this bound can be too weak to explain the empirical success of diffusion models. So, for example, if we look at typical image data sets, you can see here what the intrinsic dimension is. For example, for ImageNet, the pixel space has dimension of order 10 to the 5. Its intrinsic dimension has been estimated to under 50. So if we want to capture the very good performance of diffusion models, we somehow need bounds that scale with the intrinsic dimension. So this is often known as the manifold hypothesis. Essentially, this states that the measure is supported on a lower dimensional structure, potentially a manifold, and we're going to write little d for the intrinsic dimension of the manifold, okay? And we're assuming that that's much less than capital D. So the idea then is, can we get, or the question is, can we get bounds that scale in the intrinsic dimension? And straight away, there's a couple of obstructions that may come to mind. So the first one can be obvious. The second one is a little bit trickier. So if you consider a sequence of Hilbert curves, these are one-dimensional objects, and you consider a sequence of measures supported on these things, then all of the supports are one-dimensional, but in the limit, the measure will be supported on the full hypercube of the full dimension, capital D. So without certain assumptions on the manifold and the measure, we cannot really capture the intrinsic dimension. So for example, the Hilbert curve here in the limit, it's only Holder continuous with 1 over capital D. So essentially there's no smoothness that we can exploit there. The second abstraction was first noticed by Li and Yan, and I need to explain a little bit about how these convergence bounds are derived. So essentially, when you're studying the discretization error, at some point you pick up these terms like this. So this is essentially the difference of the score at two different neighboring times, if you like, evaluated at noisy samples at the corresponding times. Okay? Now it turns out that, in fact, these terms scale like square root of the ambient dimension. So they capture the dimension of the diffusion rather than of the underlying data. To see why this happens, it's a fairly easy calculation using just the definition of the Ornstein-Allenbeck process. Essentially, we can write the Ornstein-Allenbeck at different times using the previous time steps or the clean data point x0 plus Gaussian noise. Also, we use Tweedy's formula, which expresses the score function as a conditional expectation of the noise you add to go to the noisy data point, conditioned on the value of the noisy observation. Okay, now in a recent paper with Iskander and Judy Rousseau, we've shown that actually the score function is fairly close to a rescaled version of the noise you've added, and the distance scales like square root of the intrinsic dimension. So then you can just use a triangle inequality if you want to study this difference term. You get a sum of 3 terms, one of which is scales like capital D, the other scale like little d, so it becomes clear why you pay this price. The other thing Li and Yan did is they considered a more general discretization scheme where you're allowed to use different coefficients in front of the previous time points, the score approximation, and the Gaussian noise. And in particular, they identified a unique choice that can remove the capital D term. And they managed to prove bounds that scale like the 4th power of the intrinsic dimension. Now, ignoring constants, for example, for ImageNet, this is in general, it's much better than capital D, but for ImageNet, for example, D to the 4th is larger than capital D. So essentially, there's still something missing. So if you're wondering why this works, then hopefully this picture can offer a little bit of insight. Hopefully you can read it. But the idea is that when we're discretizing, we're trying to express the score at time t plus gamma as a function of the score at a previous time step. And when we do this, we pick up this term here, the highlighted term, which is precisely a noise term z gamma. Okay? And we know that that scales like capital D. So, however, we can modify the score approximation that we use in the backwards SDE to remove that term. Essentially, we want to remove this normal direction, this red arrow, and then that completely removes the capital D contribution. So essentially, we get a different score approximation that serves the purpose of being plugged into the backwards SDE. It's a piecewise linear SDE, so we can solve it using similar techniques to the standard one. And now the question is this some sort of like strange scheme that no one is using? The answer is no. In fact, this recovers the original DTPM scheme from the paper of Ho, Jane, and Nabil from 2020. So it's not just some crazy scheme that no one is using. It's just that if you follow the standard SDE score-based generative model and you use the Euler scheme, you necessarily pay this capital D price. However, if you go back to this, you can save yourself the trouble. So we've got several technical assumptions. Essentially, we're assuming the manifold is smooth. We're assuming the measure is smooth and the density is upper and lower bounded. We assume a certain scale beyond which the manifold looks locally flat, and some other technical assumptions on, let's say, the volume of the manifold and so on. And this is the result. Essentially, if you fix a tolerance and we know that the error in the score, at least at the discretization point, is bounded above by epsilon score squared, then we can control the KL, and the interesting term here is this one, which scales linearly in the intrinsic dimension. There's also a logarithmic term in the ambient dimension, but that's typically not that large. So if we're interested in iteration complexity, essentially to achieve a threshold of epsilon squared in KL, we need d over epsilon squared. And it's sharp in D. Again, the Hilbert curves can serve to, Okay, so essentially the idea for the proof, very quickly, is that using the new score approximation, the difference becomes a difference of martingale increments, and that essentially buys us a lot of real estate, because we can use the fact that martingale increments are correlated, and essentially the whole proof falls in place in just a few lines. So it's just simple substitution. We get the linear dependence. And we can also get bounds in TV, but they're not sharp. There's more, the sharper bounds that have come out recently, essentially they can save a factor of epsilon. And I think one of the speakers might talk about it later today. Thank you very much for your attention.
Questions for George? Okay, I have one. So do you think some of the technical assumptions are removable, or do you think to get this like optimal linear and D rate, like you kind of need all of them?
You can, but you'll need to replace them with something else. So perhaps you don't need a manifold. You can have something that's got Hausdorff dimension. So the smoothness might not be exactly necessary, but it does help put things together.
Makes sense.
Thank you for your talk. I'm wondering if the intrinsic dimension in your paper is the same as the dimension for like a smooth manifold, like the dimension in the mathematical sense.
It is the dimension of the manifold.
And how do you test the intrinsic dimension of your data?
No, we don't test it. So we don't need to. We're not adapting to the dimension of the manifold. We don't need to know it a priori. So it doesn't appear anywhere in the algorithm.
Okay. Yeah. Thank you.
Okay, let's thank George in that case. Okay, the next talk is on learning general Gaussian mixtures with efficient score matching. This is a paper by Sitan Chen, Vasilis Kontonis, and Kulin Shah. Holden will be giving the talk on behalf of them.
Okay, great. Okay, so this work gives some of the first end-to-end guarantees showing diffusion models can learn an interesting family of distributions, in this case, mixtures of Gaussians, more efficiently than prior methods, even those from TCS. Okay, so I'll very quickly go through the setup of diffusion models just to set up our notation. So we have a data distribution. We add noise to it until we get a pure Gaussian. Let x0 be a draw from the data distribution P0. And then I'll let PT be the distribution after time t of noising. So big T is large enough so that PT will be close to a Gaussian. Okay, and we can write this as a SDE. We use the Ornstein-Uhlenbeck process for the noising process. Then we can define a reverse process, which will denote by x0 backwards. We start from a normal distribution. We run the reverse SDE, in which we need this new term that is the score function, the gradient of the log PDF at time t. Okay, so then we can follow this to get a sample from the data distribution. Okay, so all this can be encapsulated by a long line of theory work that says that as long as you can solve the score matching problem, then you can learn to generate new samples from the distribution. Okay, so more precisely, as long as you have bounded variance for the data distribution and an epsilon approximate score function for the different noise levels in this L2 sense, then you can get a bound for, if you run this reverse process, how close the sample distribution will be to the data distribution. Okay, so as long as you choose your epsilon for your score function approximation small enough, then you can get the TV distance within epsilon. Okay, and then we can also learn this. How do you use this in practice? You have to learn the score function. And there's a way to learn the score function through a denoising score matching objective. Okay, so the idea is that you want to, so when you generate the data, you have your X, and then you add your Gaussian noise. Okay, essentially the score is trying to recover the negative direction of the noise. Okay, and this makes sense because you can think of the score function as moving in the direction of higher probability density, so that's negating the score. Okay, so the minimizer of this is exactly the score. However, this now begs the question of when can we provably efficiently learn the score function? Okay, because all the current results really require strong structural assumptions on the data. For example, the distribution being a mixture of two Gaussians. Okay, and so this work shows that we can actually learn the score function and hence get an end-to-end result for learning with diffusion models in the case of a mixture of general Gaussians. Okay, so here's the setup. We have unknown Gaussian mixtures. We have some weights, lambda I, some unknown means, mu I, and covariances qi. Okay, here k is the number of components, and d is the dimension of the data. Okay, so this has been studied by a long line of work in theoretical computer science. The result here of learning a general mixture goes through parameter learning, and the best known runtime known here is on the order d to the k, 1 over epsilon to the k to get epsilon in TV distance. Note this double exponential dependence on the number of components. There are computational lower bounds based on statistical query complexity and cryptographic lower bounds that get, let's say you need a runtime on the order of d to the k. Okay, so there's an exponential gap between these two bounds. Can we close this? Okay, so the result here is that, yes, under some conditions, namely with this bounded condition number, bounded radius of the means and covariances, and a minimum mixing weight assumption, then we can, using a number of samples that's exponential, or d to the poly k tau over epsilon, there's a diffusion-based algorithm that runs in time polynomial in the number of samples, and samples from a distribution that's epsilon close to the true mixture of Gaussians. In particular, if these other parameters are constant, this is singly rather than doubly exponential in the number of components k. Okay, and in particular, if we think about the case where k is log d, then comparing this to the previous parameter learning methods based on moment matching, those require exponential time, while this only requires quasi-polynomial time. Okay, so now let's talk about the ideas of the proof. So the idea here is to use polynomial regression. So we're using this reduction from sampling to learning the score function at various noise scales. Okay, so now let's fix a noise scale and try to learn the score function at that noise scale. Okay, so we want to learn the score function. We're going to parameterize it or approximate it with a polynomial of degree L. Okay? If we can do this with degree L, that gives a learning algorithm with complexity d to the L, okay, by linear regression on the polynomial features. Okay, so let's consider this polynomial approximation problem. Let's just look at the very simple case of a mixture of two Gaussians that are spaced r distance apart. Okay, we can draw this graph, the score function. We can compute exactly some function of tanh. Now, it turns out, however, that to approximate this pointwise in an interval negative m to m requires a polynomial of degree on the order of m. Okay, so if r is our radius, this needs a polynomial of polynomial in r degree. Okay, so this seems bad. However, we note that we actually don't need a pointwise approximation of the score function. Okay, remember our objective function is this L2 objective. We only need our score function to be accurate in areas where we have good probability density over the data distribution. Okay, so in this case, the density is concentrated on these two parts on which the score function is approximately linear. Okay, so in this case, we can, the idea is like when this polynomial approximation is hard, we can actually cluster these Gaussians, and then we can try to fit a different polynomial for each cluster of components. Okay, in this case, each part looks approximately linear. So this motivates the algorithm, which is first cluster these different components crudely, and then looking at the points within each of these, we learn the piecewise polynomials by linear regression on the polynomial features. Okay, so to summarize, these authors give a new algorithm for learning Gaussian mixture models based on efficient score matching. This is, diffusion models are empirically very successful, and they actually give new theory results in this case. This is a first example of diffusion models achieving a state-of-the-art theoretical guarantee for unsupervised learning tasks. And in particular, they improved the runtime from doubly exponential in the number of components to exponential under this condition number assumption. Some open problems here are improving this exponential dependence on epsilon and the condition number. So there is a 1 over epsilon in the exponent, which I believe comes from the degree of the polynomial you need to take. And then another problem is, can you use this to properly learn a mixture of Gaussian using this diffusion sampler rather than currently this improper learning? Okay, thank you.
I don't know if you've been authorized to answer questions on behalf of the authors.
You can ask questions. I will preclude with I'll answer to the best of my ability.
All right, Holden will try to field questions. I can ask I think an easy one. So what breaks if you drop the conditioning, I guess?
I'm not completely sure, actually, but I think so. The degree of the polynomial, so whatever appears in the exponent comes from, I believe, comes from the degree of the polynomial you'll need to take. Yeah, so I think it makes things worse conditioned, so you need a higher degree polynomial.
I see. Okay, let's thank Holden for his talk on behalf of the authors. Okay, so the next talk will be by Siamantak on spike and slab posterior sampling in high dimensions.
All right, yeah, so thank you for the introduction. And I'm going to talk about our work on spike and slab posterior sampling in high dimensions. This is joint work with Professor Purna Sarkar and Professor Kevin Tian, my advisors, and my colleague Yusong Zhu. All right, so I'm going to first motivate why sparsity is relevant in the Bayesian sense. Well, sparse linear regression is a pretty fundamental problem. It's well studied in high-dimensional statistics. The setup is as follows. You have a vector theta star, which is sparse in d dimensions. And you have a measurement matrix X, which is n by d. N is the number of measurements here. You observe these noisy observations, x theta star plus noise. The noise is typically assumed to be Gaussian. And in the frequentist setting, classical results show that polytime recovery is possible for this theta star in an appropriate norm, either the L2 or the L infinity norm, up to the scale of the noise, even when the number of observations is much, much smaller than d, roughly the support size of theta star. However, one problem that remains here is that this is not able to model uncertainty in the coordinates. Particularly, some coordinates of theta star can be very close to the noise level, and that's where the Bayesian setting comes in. So in the Bayesian setting, you have a prior from which you have sampled a theta star. That prior is mostly supported on sparse vectors. And given this theta star, you again generate the observation similarly. You have y being x theta star plus noise. And so you're given this x and y. And your task is now to sample from this posterior, given this x and y, which is given by this expression here. And a choice of a prior which is popular in the literature is the spike and slab prior, which essentially goes at each coordinate and performs a coin flip to either choose whether it's a spike, which is a direct delta at 0, or it's a slab, which is any diffuse density, for example, a Gaussian. And if you sample in this way, then the expected sparsity of your vector is the L1 norm of Q, which we denote as K. And this is assumed to be much smaller than D, and we want our sample complexity for this posterior sampling to be dependent on this sparsity parameter K here. Okay, so why is this hard? Well, if you simplify the posterior that you have on the previous slide, then it can be shown that it's actually a mixture of Gaussians. But it's a mixture of Gaussians over D choose K candidate subsets, which are candidates for the support of theta star. And therefore, it's not unimodal. I'm going to give details on the expressions in later slides, so not going to that right now. But even so, this problem has been addressed in the literature quite extensively. So broadly, we found three different kinds of methods. The first one is are the MC-MC-based methods, which try to approximate this complicated posterior by a unimodal distribution. However, to do that, they require certain assumptions on the signal strength being sufficiently large. The second one are these variational Bayes methods, which also try to approximate this by a simpler posterior, but end up solving an optimization problem which can turn out to be non-convex. And more recently, there's this paper by Montanari and Wu, where they attempt this multimodal sampling problem by a measure decomposition, where they introduce an extra variable and try to marginalize over it later. But they end up requiring sample complexity growing linearly with the dimension d instead of depending on the sparsity k. And so that's what motivates our question here. So we want a polynomial time sampler that works for this spike and slab posterior. It must use sublinear measurements, and it should work for arbitrary signal-to-noise ratios, not requiring particular assumptions on the signal strength. And the canonical assumption that we work with is the popular RIP assumption, or the restricted isoperimetry assumption, which intuitively states that for all sparse vectors, X behaves like an isometry. Under this assumption, we're able to show that if the slab component is a Gaussian, then we're able to sample in polynomial time, given sample complexity roughly k cubed, with polylog d samples hidden, and there is a near linear variant with k to the 5. And similarly, for the Laplace case, we're able to extend these results, but there we end up requiring certain bounds on the signal strength. All right, so at a high level, our algorithm is very simple. It's rejection sampling. So as in previous methods, we also try to come up with a posterior which is easy to sample from. But we don't try to find an optimization problem and optimize the posterior that we get. Instead, we try to come up with a simple posterior and prove that it has bounded density ratios, which enables efficient rejection sampling. So I'm going to describe some key ideas that went into building that algorithm. So the first one is to approximate our posterior. The choice of the approximation is a product distribution. So to do that, one of the key observations is the RIP property, which we have just seen before. And using that, we can we essentially substitute at all the right places this expression of X transpose X for sparse subsets S to be replaced by the identity. The second key observation is that to implement rejection sampling efficiently, we need these rejection ratios to be bounded. And to do that, if we naively don't process the posterior in any way, then it becomes intractable. And so I'm going to deal with that in the later slide. But we perform some denoising where we use the frequentist estimator and try to include those coordinates into our solution and then only sample the remaining ones. Finally, we show a posterior contraction result where we show that the posterior mass is concentrated mostly on sparse subsets. And this enables the sampling from the product distribution to be implemented efficiently using a dynamic programming-based algorithm. So I'm going to start by first giving some intuition on why denoising is necessary here. And so as promised, this is the expression for the posterior. I don't want you to get distracted by these weird expressions. But to gain intuition on why denoising is necessary, let's focus on the vector BS, which is roughly X transpose Y. Now, a naive approximation here would be to substitute Y to be X theta star plus noise, which is the model that we're working with, and then use the RIP property and the sparsity of theta star, replace X transpose X by identity. If we go ahead with this approximation, we end up with BS being roughly theta star plus some noise term. However, this is not sufficient to get a multiplicative approximation of the density, which is crucial for rejection sampling. And the reason is that even after doing this approximation, the coordinates of theta star can be very non-uniform. And that scaling makes the scale of BS in general too large unless we place some assumptions on the signal strength. And this approximation does not hold. And the solution here is to include the large value coordinates using the frequentist estimator, and then that levels out the ratio so that rejection sampling works in polynomial time. So this is a high-level idea. And then I'm also going to talk briefly about the proof for posterior sampling, because we found that to be very neat and very self-contained. We'll need a result from Jalal et al. For this. So that result is pretty general. You have a metric space and a distance metric D on that. A prior exists on that space, and you sample a theta star from the prior, and you generate data using this theta star. So this is a general version of our model as well. Then they state that if you have an algorithm that is able to process this data and give you an estimator beta, such that it's epsilon closed with high probability, then the posterior sample must also satisfy this property, maybe with a factor of 2 epsilon. And so this is a pretty strong and general result, and we use it to show contraction for our posterior as well. So how do we do that? Well, here is the entire argument, so it fits on one slide. You start with the metric being the Hamming distance. So you're sampling supports and trying to show that the support of the posterior is, of a sample from the posterior is sparse. The estimator we'll just assume to be always the null set. Now, what you do know is that the prior from which the theta star was actually sampled is a spike and slab distribution. And therefore, it's a sum of Bernoullis with parameters qi. And standard Chernoff bounds yield that the size of S star cannot be much larger than order k, which is used here. And so now we are free to apply the proposition that we just saw on the previous slide. Now, distance between the estimator phi and the true posterior S star is already order k, and so posterior sample must satisfy the distance being twice of that, so which is written here. And the conclusion that S is actually small then follows from triangle inequality. So this is the entire proof. And yeah, finally, I'm going to wind up with some conclusions and future directions for which we are thinking of. So we showed that in k-cubed polylog D samples across all ranges of the signal-to-noise ratios, a polytime algorithm exists for spike and slab posterior sampling. There's a near linear time variant if the number of samples are allowed to go up to k to the 5. And this framework extends to the Laplace cases as well. Some directions which we are interested in right now are whether we can bring this k-cube down all the way to k, which is the information theoretical limit, and also maybe consider prior itself on Q. So instead of the probabilities Q being fixed, they are coming from another prior. The third one is to generalize to beyond just the Laplace or the Gaussian case to other general general densities as well. And finally, we wanted to explore whether this algorithm, how it performs on real high-dimensional regression tasks. Thank you.
Questions for Siam Mantak? I can have one. So I guess you have a sense of when this problem is kind of like hard. So in some sense, like if your SNR is sort of like very low, then your posterior is like sort of like super diffuse. In this case, it's not super concentrated, but I guess it's kind of concentrated enough that your frequentist estimate kind of gives you like a warm start enough to kind of do something. Do you have like a sense of what, if there's like a range where it's plausibly hard?
So I guess previously what's been shown is that if the SNR is too low or too high, then the problem is kind of easy to solve, because if it's too high, then it's unimodal, and if it's too low, as you said, it's diffuse. We are kind of interested in this intermediate regime, and that's why the denoising procedure is kind of necessary to kind of include the high-value coordinates beforehand so that we are able to work with what remains. So we are actually in the domain where it is hard because we're not assuming anything about the signal-to-noise ratio.
So does that mean that basically the problem is kind of like polynomial time solvable in all regimes of SNR at this point?
At least for the Gaussian prior, definitely, yeah.
It's very neat.
Yeah.
And what about without the RIP condition? So without RIP, would you expect there's computational versus statistical trade-offs for the sampling?
Yeah, actually, that's a good question. Actually, I'm not aware of like whether even in the frequentist setting, whether sparse recovery would work without and the RIP assumption. So yeah, we haven't explored whether that can be relaxed to something weaker than that as of now. Yeah.
Okay, let's thank the speaker one more time.
Thank you.
So the next talk is actually a pre-recorded talk because none of the authors could make it. So it'll be on low-dimensional adaptation of diffusion models, convergence, and total variation.
Hi, everyone. Today, I'm going to present our paper, Low-Dimensional Adaptation of Diffusion Models, Convergence in Total Variation. This is joint work with Jiadong Liang, who is a postdoc in our department, and my advisor, Yuxing Chen. Here's a link to our paper. In this paper, we will focus on generative modeling. So in the generative model, we're given some training data xi, IID from some distribution in Euclidean space, like P data. And we aim to use this training data to get a generative model to generate new samples Y from the same marginal distribution P data. And to be more specific, we will focus on score-based generative model. So the generative model is a composition of two parts, a forward process and a backward process. In the forward process, we will start from some target distribution with a random variable x0, and we will diffuse data into noise. We're consistently adding noise into the data to convert it into a pure noise. And in the backward process, we want to convert pure noise into a data-like distribution. So we'll use some denoiser to convert yt to y0, and hopefully y0 is very close to x0, so we can use it as a sampler. So the thing we need to construct this denoiser is called Stein score function, which is a gradient of log density function. So we can learn this score function from the forward process and use it to construct our update in the backward process. And our target goal, final goal, is to make yt in distribution almost same as xt and use y0 as our sampler. There are two mainstream diffusion models used in practice. The first one is a stochastic sampler, which is called denoising diffusion probabilistic model. And second one is a deterministic sampler called denoising diffusion implicit model. We'll refer to this sampler as DDPM and DDIM in the following talk. And in the previous work, the state-of-the-art result tells that with perfect score estimation, both DDIM and DDPM sampler yield accurate epsilon accurate sampler into the variation in approximately d over epsilon iterations with some logarithm term omitted. Here, d is the ambient dimension of the target distribution. And the following question is this upper bound tight? And typically in practice, people found that d over epsilon iterations are way too slow than practice. For example, in the ImageNet, the d, which is the dimension of the data, is over 100,000 dimension, 100,000. And the intrinsic dimension here is approximately k equals to 43, according to this paper. And in practice, DDIM or DDPM sampler yields good sample in only hundreds or even tens of iterations. So it seems that the iteration complexity should be proportional to k instead of d. So this motivates our problem. Can diffusion model adapt to intrinsic low dimensionality? So we can interpret this problem from the lens of SDE or ODE. First thing is the forward process. So we can regard the diffuse data into noise as a solution to this SDE, which is diffusion process. And it is widely known that there exists a reverse time SDE with the same path distribution as forward SDE. And if we time discretize this SDE, we get the DDPM sampler. And the similar story holds for DDIM. There exists a reverse time ODE with the same marginal distribution. And DDIM is a time discretization of this ODE. So from this perspective, we can see that in continuous time limit, sampling is feasible once the score function are available. So we'll use this score function to construct this reverse process to get the sampler. So there are almost no restriction on the target data distribution. And the only thing we need is an accurate score estimation. And since the sampler is a discretization of the differential equations, the discretization scheme matter. So this converts our problems to the following question. So which discretization makes the influence of discretization and score estimation adapt to low dimensional structures? So before state our result, we first need some concept of the intrinsic dimension. So we assume the target data distribution is set to have intrinsic dimension k. So this k is defined through some entropy argument. The log epsilon covering number, epsilon 0 covering number of the support of data is smaller than k times log 1 over epsilon 0. So we will call k to be the intrinsic dimension. And this concept is compatible with many widely used dimensionality. For example, the dimension of the linear subspace, the dimension of Riemannian manifold, and also some concept used in the statistics like doubling dimension and Minkowski dimension. So it is a very common concept of the intrinsic dimension. And beyond this assumption, the only assumption we need on the data distribution is it is almost surely bounded by some polynomially large diameter for arbitrarily large constant CR larger than 0. And also, since we're used to do score estimation in the forward process, we assume the score estimation with L2 error smaller than k squared. So actually, in our paper, we use some different forms to characterize the score estimation error. And here we only use L2 error to simplify the presentation. And our main result is about the convergence of the sampler into the variation. It's that both DDP and DDIM sampler in their original form yield a TV distance smaller than epsilon sampler in approximately k over epsilon iterations with some logarithm term omitted. So here the iteration complexity only depends on k instead of d, which means that it shows some adaptivity. Here the original form means that we use exactly the same coefficient as the paper proposes to algorithm. Specifically, we'll choose this type of coefficient as our sampler. So these coefficients are originally derived to optimize variational lower bounds. So here we derive them from the pure differential equation perspective and get exactly the same result. And another thing I want to mention that is there's some previous result on the convergence in KR divergence. And if we apply their result plus the Pinsker inequality to get our this type of TV convergence theory launch, actually our bound is tighter than that bound. So if we use KL divergence plus Pinsker, we'll get approximately K over epsilon square iterations, which is much larger than K over epsilon iterations. And another thing I want to mention here is, since in our algorithm, we need to choose some specific coefficients, we also prove that this choice of coefficients is crucial for the adaptivity. So we will focus on this type of sampler, which each update is a linear combination of the sample, score function, and the pure independent Gaussian noise. So we give some lower bound for this type of sampler. We prove that there exists one distribution, even when we start from xt equals yt at time t, and at time t minus 1, the TV error is larger than square root d times the function of the coefficients. So to avoid scaling in D, which means no adaptivity, one needs the red term to be approximately 0. Luckily, both DDIM and DDPM sampler satisfy this. And the takeaway is, if we want to get an adaptive sampler, adapt to the intrinsic dimension, the sampler must be close to the DDIM, DDPM sampler. And to give you some intuitions of why this is true, we need to connect it back to the SDE and ODE. So here I present the reverse time SDE with the same marginal distribution. And to get the adaptive sampler, we need to reparameterize this SDE with the mu tx, which is the post-error mean of the forward process. So after this reparameterization, we can discretize it with some discretization scheme, for example, exponential integrator scheme. And then we can solve this SDE analytically to get the DDPM sampler. So why DDPM works? Here mu t is the post-error mean, so it is a projection onto the low-dimensional structure, which enhances smoothness and give you some adaptivity to the low dimensionality. And luckily, the same trick works for DDIM, so we use this type of argument to get our results. Concluding remarks, our paper shows that diffusion models adapt automatically to unknown low dimensionality. The choice of coefficients matter for efficient sampling, especially adapt to the low dimensionality. And the DDPM and DDIM sampler is adaptively discretized reverse time SDE and ODE. And we use this trick to prove the result in our paper. You can see the details here in our paper. Thanks for your attention. Hi everyone, today I'm going to present our paper, Low-Dimensional Adaptation of Diffusion Models.
Is there Q&A for this? Or? Oh, the author is on. Okay. Okay. All right. I think that's you, Holden. Oh, okay. Maybe. Jihan, can you hear us? Hello?
Yeah. Hello.
All right. Questions about Jihan? Okay, I can ask one. Can you talk about like if there's any sort of like hope for similar kind of adaptivity to other low-dimensional structures other than the covering number?
Yeah, I think covering number actually is a very like widely used thing, because we talk about it's like consists of concepts like dimension of manifolds and other things. Yeah, but if you can have some like more geometric assumptions, I think you can adaptive to it, but you need some like strong assumption on it.
And I guess, is it sort of like clear which notions of low dimensionality play well with sort of like the denoising score matching, I guess?
Yeah, we find that covering number is actually a a kind of suitable concept. Yeah, but I think there's some chance to generalize to some like geometric assumption.
Okay, cool. Other questions? All right, let's thank Jihan one more time.
Yeah, thank you. Dimension of the target distribution. And the following question is this upper bound tight? And typically in practice, people found that the over epsilon iterations are way too slow than practice. For example, in the...
Sorry, okay.
All right. Next up, we have Holden again, talking about learning Gaussian mixtures with score matching and diffusion models again. But this time, he's an author of the paper, so you can ask him as many questions as you like. Take it away, Holden.
Okay, this is joint work with Kashar Gatmary and Jonathan Kellner from MIT. Okay, so the first picture, this is drawing a mixture of Gaussians with diffusion models, so giving it the proud of, comparing it to finding needles in haystacks. Okay, so diffusion models are empirically very successful at learning distributions. So the way they work is we take pure noise, we follow some backward process to get a new sample from the data distribution. This backwards process requires this score function, which is the gradient of the log of the PDF of this noisy distribution PT, as P convolved with Gaussian noise. Okay, so now the theory is well understood that there's a formal reduction, that sampling is as easy as learning the score function. So as long as we have estimates of these score functions at these different noise levels, then we can get an accurate sample from the data distribution, and that has been made very nicely quantitative. However, a big unsolved question is for what families of distributions can we actually learn these score functions efficiently and so get an end-to-end result for learning distributions with diffusion models. This has proved surprisingly elusive, even to try and learn families of distributions that we know we can do with other algorithms from TCS. So what is a good family to look at? Mixtures of Gaussians. Okay, so in this work, I'll consider isotropic mixtures of isotropic Gaussians, so unknown mixing weights and means, but all these Gaussians have identity covariance. Okay, so importantly, I'm doing distribution learning rather than parameter learning. So in this way, I don't require any separation conditions between the means. Remarkable work by Diakonikolas and Kane showed that you can use algebraic methods to get quasi-polynomial time and sample complexity. And we showed that diffusion models can also learn with quasi-polynomial time and samples, giving a completely different approach to this problem. And this is a first end-to-end result for learning a non-trivial family of distributions with diffusion models. So there's been concurrent work that's previously presented, which considered the case of where this covariances can be different but have to be well-conditioned. So in comparison, they have a runtime that's exponential in the number of components, while we get a more efficient quasi-polynomial bound under this isotropy assumption. So we both use polynomial approximation, but in different ways. So these results are incomparable. Okay, so here's our main theorem. So we actually prove a generalization. So we can think of a mixture of k Gaussians as a discrete probability measure on k points convolved with a Gaussian. Okay, so the way I'll generalize this is to a non-parametric family where we want to learn distribution that's some base distribution Q0, think of that as the means, convolved with a identity covariance Gaussian, where this base measure Q0 is made up of k clusters. That is, its support can be covered with k balls of constant radius. We also need the assumption that each of them has its weight or its probability lower bounded by alpha min. Okay, in particular, this covers the case where Q0 is supported on k points. Okay, our main theorem is that we can learn a distribution that's epsilon close to P0 with time and sample complexity that's quasi-polynomial in the ambient dimension n, number of components k, and 1 over epsilon. And this is the first efficient algorithm in this more general non-parametric setting. Okay, so as a corollary of this, we can have a kind of manifold learning. Okay, so in a very weak sense of the word manifold, if your set M, if your base measure Q0 is supported on a set M, that can be covered with C to the D balls of constant radius, each with this probability lower bounded, then you can learn this distribution in time that's exponential in a polynomial in D. And all these results generalize if you allow the balls to be some radius r with a poly r factor in the exponent. Okay, so I'll outline the proof of this theorem. So by our reduction, we know we can sample or learn to sample random data distributions if we have L2 accurate score estimates at these different noise levels PT. So we need to learn these score functions. The first thing we'll show is that these score functions are learnable within a nice function family. Okay, show approximation result. First, we'll consider the case of one cluster when all the means are within constant radius. In this case, a polynomial of low degree, that is log 1 over epsilon degree, will suffice to approximate the score function. In the general case, we'll need a piecewise polynomial. And how do we determine these pieces? So as long as we have a set of worm starts, which I'll define later on, if we partition space according to this Voronoi diagram of this worm starts, then we can approximate with this piecewise polynomial. And so to make this algorithmic, the remaining step is to show that we can sequentially maintain these worm starts. And I'll give this denoise plus cluster algorithm to do this. Okay, so to learn these score functions, we have to first understand what the score function of a Gaussian mixture looks like. So I'll use the interpretation of it as a denoiser. Okay, so here's the setup. So our sample from a mixture of Gaussians we think of as coming from a Gaussian centered at a mean mu. We add a Gaussian to it to get our data point x. And when we run our diffusion model, we add additional Gaussian noise to get a point y. Okay, so the score function has this nice interpretation where if we take our noisy point y and move in the direction of the score function, okay, then by Tweedy's formula, this gives us a denoising effect. It gives us the expectation, the posterior expectation of the mean mu that it came from, conditioned on this noisy observation y. And if we know the parameters, we can write this out explicitly. Okay, so hold that in your head for a moment. Now, how do we show this can be approximated by a polynomial? Our key technique we use is that of noise stability or sensitivity. So the noise sensitivity of a function f asks this question: how much does adding noise to the input change the expected value of that function on average over a distribution mu? Okay, and if we can prove some kind of noise stability with respect to a noising Markov kernel k, this implies approximability by the top eigenfunctions of k, for example, polynomials, and this implies learnability under the stationary distribution of k, a so-called low-degree algorithm. Okay, this has been applied a lot in TCS, both in the case of the hypercube and for the Gaussian. Okay, so in our case, the noising operator is given by this Ornstein-Uhlenbeck process, and we can define noise stable to mean that the kind of instantaneous change in the average value of f, under adding this noise, is small on average over the Gaussian distribution. Okay, so the key theorem that we use is that noise stability implies low-degree approximability. We can find a polynomial of degree almost d such that this is the approximation we have is this noise stability divided by d. Okay, the proof of this is by expanding our function into eigenfunction or Hermite polynomial basis for L. However, the issue with this is that it requires degree 1 over epsilon to get epsilon accuracy, and whatever we get here will turn out to go into the exponent for our algorithm. Okay, so we use a higher, so our key innovation is a higher order version of noise stability in much the same way that we use, Markov's inequality with higher powers to get better concentration bounds. Okay, so in this case, we can then just take a degree that's logarithmic in 1 over epsilon. Okay, so then it remains to actually bound this noise stability. So now using our explicit form for our score function in terms of this posterior expectation, it turns out that it's really elegant to differentiate this because you just get higher moments and you can bound these with Gaussian moments. Okay, so a key, there's technical complication in that you have to change the measure to a mixture of Gaussians, and that takes some work. Okay, so that gives approximation for a single cluster. Now to go to multiple clusters, what we need is a set of worm starts. Okay, so by this I mean a set of points such that we know that every mean is at most distance r from one of these worm starts. Okay, if we have this, then we can run polynomial regression on the Voronoi diagram from these worm starts, do a polynomial regression on each part. So the only remaining problem is how do we find these worm starts? Okay, so suppose hypothetically that we have an estimated score function. Okay, we could use these to find the worm starts as follows. We know by Tweedy's formula that the score functions point in the denoising direction. Okay, so we take our noisy samples and add the score function to them. These gives us approximately which means they came from, and then we do a greedy clustering algorithm, greedy set cover with these estimates. Okay, so it turns out that this will then give us a complete set of worm starts. Okay. And then we get this at the noise level that we're currently working on. Okay, so to put this all together, we can approximate the score function with this piecewise polynomial as long as we have these worm starts, and then we can get these worm starts as long as we have a score estimate. Now you might think that this is a circular reasoning. However, it's not, because the way we're going to use this is sequentially from the highest noise level to the lowest, and we can use the score estimate for the previous higher noise level to obtain worm starts for the next smaller noise level. Okay, so this critically uses a kind of sequential denoising approach. Okay, so in conclusion, diffusion models give a new analytic proof for learning isotropic and even non-parametric Gaussian mixtures with quasi-polynomial complexity. We use higher order noise sensitivity, and this maintaining these worm starts vitally uses these denoising framework. Okay, so I think there's a lot more open questions on learning Gaussian mixtures more efficiently, having better dependence on these parameters or using structure of the Gaussians. It's an interesting question, can you do this using neural networks, and also to look beyond Gaussians for other families. Thank you.
All right, questions for Holden? Okay, I can ask one. So I guess this is kind of a very nice idea with sort of like applying the operator and sort of thinking about stability from the perspective of the operator. Like I guess if you had some, instead of like looking at mixtures of Gaussians, if you had like a mixtures of log concave distributions, could you kind of like co-design the noising process so that's kind of, so that it gives you kind of similar results for like a more complicated class of mixtures?
So the nice thing about mixtures of Gaussians, if you add Gaussian noise to them, they're still mixtures of Gaussians. Right. So you could try something with, noise stability could potentially give you something with other log concave distributions as well. You have some maybe to work with different eigenfunctions. Or I think also another issue is that the space of log concave distributions is too large to be efficiently learnable. But so maybe you want to impose more structure, like some approximate independence or something else. Yeah.
All right, let's thank Holden one more time. All right, next up we have August Chen, who's going to tell us about optimization, isoperimetric inequalities, and sampling via Lyapunov potentials. Take it away, August.
Hi, I'm August. Today I'll be presenting joint work with Karthik Sridharan. So maybe for some motivating remarks, with the rise of generative AI, which can be modeled mathematically as a problem of sampling from non-log concave distributions, as has been referred to in previous talks, this motivates the following question. So we know that a canonical Markov chain, Langevin Monte Carlo, can sample in polynomial time from measures mu, which are log concave. Equivalently, the energy function negative log mu is convex. So this motivates the question of which measures mu, which are not log concave on RD, can be sampled from via Langevin Monte Carlo efficiently. So at a high level, we established the following. We show that Langevin Monte Carlo can sample in polynomial time in dimension and inverse temperature if the energy function negative log mu is optimizable by gradient flow at an appropriate relevant temperature setting relevant for sampling. So this proves that we proved this result through establishing isoperimetric inequalities from scratch for a large natural class of non-log concave distributions, when typically you think of isoperimetric inequalities in the continuous context as holding for log concave measures. And perhaps more fundamentally, we establish direct connections between optimization and sampling at the algorithmic level. So to state these results with more precision, we need to go into some background. So in this talk, we're interested in sampling from the measure mu beta given in the Gibbs or Boltzmann form defined as follows. So it's proportional to e to the negative beta f, where f is a given function, beta is the inverse temperature, and it divided by z, the normalizing constant. So typically for non-convex f, we think of as beta increases or the temperature is lower, the problem becomes harder, at least without additional structure on f. So we work with the canonical Markov chain Monte Carlo or MCMC setup, where we have oracle access to f and its gradient. To be clear, this has been referred to in similar talks prior, but the goal is as follows. We start with an initial law pi naught and run a Markov chain to produce an iterate w after t steps. We want the law pi t of w to be close to the measure mu beta of interest in an appropriate metric between distributions. A canonical means of doing so, at least if we could simulate continuous time, is the Langevin diffusion SDE, which can be viewed as gradient flow plus noise in the form of a Brownian motion. Now, this is a natural means for solving this problem because in the limit as t goes to infinity, the stationary measure of this SDE is exactly mu beta. There are many discretizations of this SDE. Perhaps most simple is the gradient Langevin dynamics, which you can view as gradient descent plus appropriately scaled noise, but there are many other very clever, elegant discretizations. Broadly, this SDE and its discretizations we refer to as Langevin Monte Carlo. So we just referred to what happens in the limit as t goes to infinity, but we're interested in non-asymptotic guarantees. We obtain one when the measure mu beta is nice in the sense of satisfying a Poincare inequality. So this holds with constant CPI if for all test functions f, the variance of f under mu beta is upper bounded by the Poincare constant times the Dirichlet form. In this work, we adopt the convention that a smaller Poincare constant means that the measure is nicer. Now, this subsumes all log concave measures equivalently in the form we wrote earlier when f is convex, but it is more general. And its implication is exponential contraction for the Langevin diffusion in chi-squared. So see also log Sobolev inequality, which corresponds to strongly log concave measures or strongly convex f. So in this work, we pose the question of if we can show end-to-end isoperimetric inequalities beyond convexity. So as stated earlier, when f is convex or the measure mu beta is log concave, it satisfies a Poincare inequality with constant polynomial in the dimension and inverse temperature beta. So there's been a line of recent work establishing sampling guarantees via Langevin Monte Carlo, assuming you have a Poincare inequality with constant CPI. However, what does this mean when f is not convex or mu beta is not log concave? For generic non-log concave measures, the Poincare constant is at best exponential in the dimension. Here we want to ask if there are natural classes of non-log concave or non-measures or non-convex f satisfying Poincare and log Sobolev with controlled constant polynomial in the dimension and inverse temperature. To do so and answer this question, we take inspiration from non-convex optimization. So non-convex optimization, even when f is not convex, f being the loss function, there are these properties of gradient domination like PL and KL, and one-point convexity properties like linearizable/quasi-convex that yield efficient global optimization. These conditions can all be wrapped under the following hood, introduced in a work by Desai, Kale, Lee, Shekari, and Sridharan. So in particular, the condition is that f is optimizable by gradient flow if there exists a corresponding Lyapunov function phi, such that the inner product of the gradients is at least f or a monotone function thereof. So the interesting part, and why I said this corresponds to an optimizability condition, is because this condition holds if and only if gradient flow converges under fairly mild regularity assumptions on the convergence of gradient flow. And in particular, this condition covers those aforementioned canonical conditions from non-convex optimization. When phi equals f, we recover PL and KL, and when phi is norm squared, we recover linearizable or quasi-convex. So we're interested if optimizability by gradient flow can yield isoparametric and algorithmic implications for sampling via Langevin Monte Carlo. So we addressed this question in our work. In particular, we established the following. Suppose f is optimizable by gradient flow in the sense presented earlier. And furthermore, that mu beta, when restricted to a neighborhood of w star, the global minimizers of f, satisfies a local Poincare inequality with constant CPI local. So this condition turns out to be necessary if you want fast convergence of Langevin Monte Carlo. Without it, there are counterexamples. And furthermore, if f and phi satisfy some mild regularity assumptions, which are satisfied by many examples. Then we establish for beta linear into dimension, a temperature setting which we will show later is relevant for Bayesian inference. The Poincare constant of mu beta is this local CPI plus 1 over beta. So 1 over beta is what you pay to go to all of r to the d. And this local constant is actually necessary. For example, consider when W star forms a dumbbell. So even in low temperature settings where optimization and sampling are relatively comparable, once you reach that dumbbell, mixing would be poor because of poor isoparametric properties of the dumbbell. Under some additional mild regularity assumptions on F, which generalize the so-called dissipativity condition from non-convex optimization that's fairly ubiquitous, we can show that the log Sobolev constant is also controlled in a similar way. So let's talk about the implications of this result. So as a consequence, we obtain isoperimetry with controlled polynomial constant for a host of non-log concave measures, in particular when f is PL, KL, or linearizable / quasi-convex, for example. So an immediate implication, therefore, is from efficient sampling from arbitrary initializations for various non-log concave measures. But perhaps at a deeper level, this shows implications at the algorithmic level in that we connected optimizability via gradient flow. Recall the condition presented was a form of an if and only if condition to sampling via Langevin Monte Carlo. I should also mention there's been concurrent work for focusing on PLF, in particular by Gong, He, and Shen, and also concurrent work on PLF by Chue and Strom, establishing PI and LSI in the ballistic limit, which is when beta goes to infinity. So I said that the temperature setting here is relevant for inference, and here's why. So let's suppose we observe n data points y and a matrix x, and in the setting of high-dimensional regression. So sampling in this setting was considered, for example, by recent work of Montanari and Wu. So we have a prior pi on W, and we're interested in sampling from the posterior mu of W, given the data y and x with asymptotics as n over d rows proportional to each other, to some constant. So it turns out the posterior in this problem will be at temperature beta equals omega of d. So here, beta is this term, and the function f is a form of regularized empirical loss. So we can interpret our result, therefore, in the language also of Bayesian inference. It says in particular that if regularized maximum a posteriori is optimizable by gradient flow, in particular that f, then MCMC methods, namely Langevin Monte Carlo, can efficiently sample from the posterior. Now I'll get into some further results on weak Poincare inequalities. So in many works in non-convex optimization, optimizability only holds from a good set of initializations. There is a small bad set S. The good thing for optimization is that if you initialize at random with high probability, your initialization starts at a good set. So we can optimize globally in many such examples, and examples are in those papers. We're interested in what we can say about sampling in this setting. So here, Poincare and log Sobolev don't hold because you don't have mixing from all initializations. But we might hope for a mixing from a suitable warm start. And indeed, in such a setting, we'll establish that a weak Poincare inequality holds, which indeed implies sampling from suitable warm starts. In particular, our result is as follows. Suppose the same conditions as our prior result hold, except now that optimizability condition, for example, PL or KL, only holds for all W not in some bad set S. Then again, for inverse temperature beta linear in D, then mu beta satisfies a weak Poincare inequality with this so-called weak Poincare constant comparable to what we established earlier, and the error term in the weak PI or weak Poincare inequality corresponding to the size of the bad set S under mu beta. This implies sampling up to accuracy or error delta from warm starts. And interestingly, or as we would like, it captures the picture from optimization. Because if S here is small, then the error term delta is small. We can show it's exponentially small in many natural cases, and therefore, we obtain sampling up to that small error. Furthermore, we prove the weak Poincare inequality with a novel simple proof via Lyapunov functions, which might be of independent interest. So thanks for your attention. This is summary of the results.
Thank you. Yeah, very interesting talk. Just wondering, so these conditions, do they allow F to have local minima? Not the first one, but the second one, does it?
Yeah, it allows F to have local minima. Actually, you don't need something like strict saddle. It would be fine, as long as the size of S is small under mu beta.
I see.
Yeah, thank you for the talk. I was wondering, maybe it will be a bit naive, but like in optimization, when you have quadratic growth, you have like a set of minimizers, let's say manifold, and quadratic growth have some exponential convergence. And I think I saw a presentation of Austin Strom, and he was talking that by his papers, there were no such result for a measure, let's say, that supported like this kind of quadratic growth around the set. And does your paper does something, you have something like that? Like exponential convergence in that case?
In some sense, yes. So we establish a log Sobolev inequality under such conditions. Okay. And then you get exponential contraction if you can do continuous time sampling, like for the Langevin diffusion.
Thank you.
All right, let's thank August one more time. And the final talk is also pre-recorded, right?
Generalization error bound for denoising score matching under relaxed manifold assumption. This is a joint work with Nikita Puchkin from the Higher School of Economics and Konstantin Yakovlev, who is also presenting this work. Let us begin with some background on diffusion models. Diffusion models rely on two key components: a forward diffusion process that gradually transforms data into noise over time, and a reverse process that learns to invert this transformation by generating high-quality data samples from pure noise. Despite the empirical success in modeling high-dimensional data, the theoretical understanding of diffusion models generalization remains limited. This brings us to our central research question: why do diffusion models perform well in practice even when the data lies in a high-dimensional space but has an underlying low-dimensional structure, as in the case of images, for example? In this work, we aim to address this question by establishing the rates of convergence that are determined by the effective dimension rather than the ambient one. Now let's turn to the formal description of diffusion models. Since the forward process converges to the standard Gaussian quite fast, one can sample